Hello everyone, can you hear me? Hello.
Yes, sir, we can hear you.
Okay, thank you. So we'll wait for a few minutes more and then we'll start. Let others join. Good evening all. I think my screen is visible and I am clear to all of you. So I once again welcome you to the interaction session for this NPTEL course Experimental Physics 1. Myself Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today we will be covering a few experiments that you have been discussed in the week's lectures contents. So first we will discuss about determination of Young's modulus of elasticity, and we'll solve a few problems related to this calculation of Young's modulus of elasticity. Then we will discuss about spring constant of a given spring, and then moment of inertia of a flywheel. So now talking about the first experiment of today's discussion. It is determination of Young's modulus of elasticity. I think all the experimental procedures and how you will do experiment, you all this have been covered in the lectures. Now we will discuss a few things related to this elasticity, how this Young's modulus of elasticity comes into picture, and then we will solve a few problems related to this Young's modulus of elasticity. Now, talking about elasticity, it is the response of a body to an applied force or torque, because we know whenever a force is applied on a body, it results in its change in shape and size unless it is moving. If it is moving, if it is not moving, then it will start to move also. But if the force is not if the force is a different types of force, or maybe we can apply torque, then there will be some deformation in the body, or body will respond to this particular applied force or torque. So on basis of this response, we have classified materials into mainly three types. One is rigid body, which generally shows no response to so particular type of applied force or torque in terms of any deformation in the body, because the force of attraction between the molecules constituting a body is very strong, or the strength is quite high. And another is elastic body. It has response, it undergo deformation, but however, after the application of the force, when we turn off the force or torque, then the body comes to its original position. And another is plastic body, which shows a complete deformation of its shape. So now when we are talking about deformations produced in a body, so the deformations are produced due to particular type of force. So we can define a quantity which is known as stress, which is dimensional equal to that of the pressure, and it is deforming force per unit area. So depending upon the type of force, we can we can divide the stress in different types. For example, one is normal stress, like the force is acting normal to a body or normal to a surface of the body, or tangential stress, which is acting at a angle or some tangent to a particular surface. And then when the force is applied and the body undergo deformation, then there will be change in shape of the body. Now this change in shape of the body, when compared to its original shape size, is called as strain, and this strain is equal to ratio of change in dimension to the original dimension of the body. So when we suppose this is a steel rod or something. So when we applied some force, then it goes undergo deformation. Suppose the deformation was such that the shape of the body was like this. Then when there was a force applied, suppose the force we applied in this direction, then there was elongation of the body. So now if you compare the two bodies, if this is the length L, then after application of the force, this length is changed, or this is the deformation. Suppose this is delta L. So stress is ratio of change in dimension to the original dimension of the body. So if you see here the change in dimension is delta L and the original length is L. So this is called as strain. So as you can see, both delta L and L are same in dimension. So basically strain is a dimension less quantity. Also, depending upon the type of dimensions involved, the strains are classified into different types. For example, what we discussed here is an example of longitudinal strain. Then there is volume strain. Suppose the force is applied in all the directions to a body. Suppose we are pressing a ball from all the directions, then the ball will undergo its change in volume. Then the volume strain will come into picture, and there is shear strain, and the fourth one is lateral strain. For example, if suppose since it is a solid, then it will undergo deformation, but not undergo so much deformation that the volume of the body changes. So if it is being elongated in a particular dimension, it may be that its thickness, that is D, will be also affected, and this will be D prime. And here in this case, D prime will be less than D, because the body is being elongated in other dimension or other direction. The length is increasing, but the width of the plate is decreasing. So if the change in one dimension causes the change in other dimension, then the lateral strain comes into picture. So there are different types of stress and strains. And then talking about Hooke's law, it states that strain is directly proportional to strain. So the amount of stress or force per unit area is directly proportional to the change in shape or amount of deformation caused in a body. So if you see, we can write it stress. The ratio of stress and strain is constant, and this constant is known as elastic modulus or modulus of elasticity. It basically gives an idea about the elastic property or elastic nature of the body. So uh, how a body behaves to a particular type of deforming force or undergo any deformation. So depending upon the type of stress and strain, because as we saw here, there are different type of stress and also there are different type of strains involved in a particular context of the thing. Then the modulus of elasticity can also be classified in different types. Then there are Young's modulus of elasticity. As you can see, Young's modulus of elasticity is mainly for longitudinal strains, and it is divided by longitudinal stress divided, and it's the ratio of longitudinal stress per longitudinal strain. Then another is shear modulus of elasticity or rigidity. So since so this corresponds to volumetric strain. So this is ball stress. Suppose this is a quantity, then we applied some stress and it undergoes change in, then it undergoes the change in volume. Suppose so it will get contracted and there the change in volume is del B. So the bulk stress will, suppose bulk stress is P, then the volumetric strain will be del B by B. So it will be PB by del B. Since this volumetric strain has no unit, any type of strain, this strain or this strain or this shear strain, they have no dimension or they have no units, then uh, we can say that the unit of or dimension of elastic constant or modulus of elasticity is equal to the dimension of stress. Stress means the dimension of pressure or force per unit area, or you can Newton per meter square or dyne per centimeter square or whatever it may be. Then calls bulk modulus for shear strain. Then this is shear modulus, this is bulk modulus, then it is shear stress divided by shear strain. So there are three types of modulus of elasticity. So in the current discussion, we are interested in this Young's modulus of elasticity. And if you remember the experiment you have performed, you have taken a, a, a long bar or a steel bar, and you have assumed that the length of the steel bar is very large in comparison to the thickness or width of the bar, because in that case there will be the dominating factor will be the longitudinal stress and longitudinal strain. So the experiment has performed to calculate the Young's modulus of elasticity, and you all know about the experiments. Then now let's solve a few problems corresponding to this modulus of elasticity. Now this problem says, what is the tensile stress developed in a wire of radius 2 millimeter when a load of 5 kg is suspended from it? Uh, so I will give you a few minutes to solve this. It is very easy question. We need to simply calculate the tensile stress, that is force per unit area, unit cross-sectional area of the wire. You know the radius of the wire and you know the weight of the body which is being suspended from it. So you will be calculating the. So now if you see, suppose this is a rigid support, and with the help of this wire we have suspended a body and its mass is 5 kg. This is a wire and it has the radius 2 mm and it is suspended from a rigid support here. Then what will be the tensile stress developed in the body? Because since the body is suspended, then there will be normal force which will be acting downwards of the body. So it will experience some force due to this mass being suspended. So as a result, the wire will undergo deformation. So what will be the tensile stress developed in the wire? So please calculate and tell me what will be the answer. Did anyone calculate what will be the tensile stress? So let's calculate. So if you see, if the mass of the body is 5 kg, then we know the force will be equal to the weight of the body. And this force is equal to mg, we know, where m is 5 and g is 9.8. It will be 9.8 into 5, which will be equal to 49 Newton. Then if you calculate stress, then for stress we need cross-sectional area, and then cross-sectional area A will be pi r square, and we know the radius of the wire is 2 millimeter. So converting it into meter, since we are calculating in Newton the force, so it will be pi into 2 into 10 to the power minus 3 square. So it will be in meter square. So when you calculate the force or tensile stress, then the stress, suppose we write it as, then it will be force per area, which is equal to 49 divided by pi into 4 into 10. I request everyone to mute themselves because it will be creating unnecessary disturbances in this session. So if you calculate, it will be coming around 3.9 into 10 to the power 6 Newton per meter square. So this is the tensile stress, because basically you must have heard about tension. Tension is a particular type of force which are generally constant in case of a straight string. So when the body is suspended, then there will be tension which will be developed in the body. So so due to this force, the tensile stress we have calculated, and it will be force per unit area, which is equal to 3.9 10 to the power 6, and the unit is always important. It is Newton per meter square. And then next question, it says the edge of a cube has length of 2 meter at a pressure of 1.02 into 10 to the power 5 Pascal, and the pressure is increased to 3.02 into 10 to the power 5 Pascals. Then each edge of the cube is reduced by 1%. Then calculate the volume strain. So here we need to calculate the volume strain, and by means of strain we know that it is the amount of deformation. So we know here the each edge has each edge of the cube has length 2 meter, and due to the increase in pressure, the cube is reduced to the edge of the cube is reduced to 1%. So there is 1% deformation in the edge of the cube. So due to this 1% deformation, there will be change in volume. So we need to calculate the volume strain, which is caused due to the increase in pressure. So I will be giving you a few minutes. Please calculate and tell me what will be the volume strain. So now let's calculate. Anyone calculated what will be the volume strain? Is there anyone who has calculated what will be the volume strain in the Q? Okay, so let's calculate. If you see here, it is given the length of each side of the cube is 2 meter. So the length is 2 meter, then the volume will be 2Q, that is 8 meter cube. So this is the original volume of the cube. And then due to the increase in pressure, now when the pressure is increased from 1.02 to 3.02 Pascal, here the pressure value we will not be using the pressure value because we need to only calculate the volume strain. But if in the question it was asked us that calculate the modulus of elasticity, then we will take this pressure. But here, since we only need to calculate the volume strain, then it will be, suppose now this is the length before deformation, this is 2 meter. But when there is deformation of 1%, then 1% of 2 meter is how much? 0.02. So it will be 1 by 100 of 2 meter, which will be 0.02 meter. So the deformed length will be delta L minus L prime will be 2 minus 0.02, which is 1.98 meter. Then volume V prime will be 1.98 Q. So we know volume strain is given by change in volume divided by original volume. So the change in volume is 8 minus 1.98 Q by the original volume. The original volume is 8. So if we calculate, it will be coming around 0.029 7. So since can anyone tell me what will be the unit of this volume strain? Yes, because the deformation is also in meter cube and the original volume is also in meter cube. So there will be no unit, or this is a unitless quantity. The value of the volume strain is 0.0297. That's it. So now let's proceed to our next question. Now the question says, what will be the density of the copper under a pressure of 10,000 Newton per centimeter square, given the density of copper is 8.96 into 10 to the power 3 kg per meter cube, and bulk modulus of copper is 1.4 into 10 to the power 10 Newton per meter square. So in question it gives, we want to calculate the density of the copper. Here the pressure is given 10,000 Newton per centimeter square, and the density of the copper is given. The density of the copper is 8.96 10 to the power 3 kg per meter cube. But when we apply some pressure, then the density of copper will definitely change. So what will be the density of the copper under the effect of the pressure, which is 10,000 Newton per centimeter square. So, and also the bulk modulus of copper is given. So we need to calculate what the density of the or the change in density of the copper. So since bulk modulus of copper is given, from this bulk modulus, since pressure given, we can calculate the change in volume. So since the change in volume we can calculate. So the change in volume compared to the original volume, then the change in density compared to the original density. So in this way we can calculate the density of the copper or change density of the copper. So I will give you a few minutes to solve this question and then I will solve. Anyone calculated? That will be the density of the copper under a pressure of 10,000. So let's calculate. So here the bulk modulus of copper is given. So we know the bulk modulus B is given as stress divided by volumetric strain. So if you want to calculate the volumetric strain, then the volumetric strain will be delta V by V will be equal to P by B. So the change in volume will be P by B into delta V. So I think here it is not centimeter square, it is meter square. So since all here are given in meter cube only, so but even if it is in centimeter square, then we can add another factor of 10 to the power something, because we will be converting it from centimeter to meter. So when you calculate, it will be how much into V. Sorry, this is so it will be V. So P pressure is 10,000 divided by bulk modulus is 1.4 into 10 to the power 10. So into V. So when you calculate, it will be V by 140. But I think yes, it is in centimeter square. So when you convert from centimeter square to meter square, then you will again multiply 10 to the power. You will again multiply 10 to the power 4 here. So it will be 10,000 into 10 to the power 4. So it is 10 to the power 10 to the power 4, 10 to the power 8, or 10 to the power 10. So there will be 10 to the power 2 in the denominator. So which will give us V by 140. So the change in volume V is V by 140. So the original volume as V, original volume was V. The change in volume is V by 140. So now the deformed volume will be V minus delta V. It will be V minus V divided by 140, which will give us 139 V by 140. So this is the new volume of the copper. Then since the volume is changed, so the density of the copper will also change because the mass remains same. So particularly the new density rho prime will be how much? Mass by new volume. It will be mass divided by 139 by 140 into V. It will be 140 divided by 139 into M by V. Now this M by V is the original density rho, and it is given as 8.96 into 10 to the power 3 kg per meter cube. So it will come around 140 divided by 139 into the original density. Original density is 8.96 into 10 to the power 3. So when you calculate it, it will be it will be 9.02 into 10 to the power 3 kg per meter cube. So this is the new density of the copper. So since here in the question it is given the bulk modulus. So what we did, so here it is given what will be the density of the copper under a pressure of 10,000 Newton per centimeter square. Given density of the copper is 8.96 into 10 to the power 3 kg per meter cube, and the bulk modulus of copper is 1.4 into 10 to the power 10 Newton per meter square. So since bulk modulus value of copper is given, we know bulk modulus is pressure divided by change in pressure divided by volumetric strain. So from this value we can determine the change in volume. So the change in volume will be P by V into original volume. So P is 10,000 and then bulk modulus of elasticity is 1.4 into 10 to the power 10. So here the quantity is given in Newton per centimeter square. So when you convert it into meter square, 10 to the power 4 factor additional will be multiplied. So it will give the change in volume is 1 by 140 times of the original volume. So since the change in volume is 1 by 140 times, then the new volume will be 139 by 140 into V. So since the volume is changed, the density will change. So if you put the value, changed volume here, then it will give us the density will be increased and it will be 140 by 139 into the original density. The original density in the question is given as 8.96 into 10 to the power 3. So when you put all the values, it will give that the new density of the copper is 9.02, which is obvious because since the pressure is applied, the volume is reducing. So due to which the density of the copper will increase and the density is 9.02 10 to the power 3 kg per meter cube. So is there any doubt? Okay, so let's proceed towards next question. So now this question says a rectangular bar of size 20 millimeter in breadth and 10 millimeter in depth and 1 meter in length is supported at its end and a rod of 2 kg is applied at its midpoint. Calculate the depression if the Young's modulus of the material of the bar is 2 into 10 to the power 12 dynes per centimeter square. Take the value of G is 980 centimeter per second square. Now, this is exactly similar to the way of doing the experiment when you calculate the Young's modulus of elasticity. We have a rectangular bar. Its the size of the bar is 20 millimeter into 10 millimeter into 1 millimeter height, and it is supported at two ends, and a load of 2 kg is applied at its midpoint. So due to this load, it will undergo deformation or it will come some distance below or lower than the original level because some force is being applied. Then we need to calculate the depression. In experiment part, we are calculating the depression and provided all the data, and we are calculating the Young's modulus of the material. But here the Young's modulus of the material is given by using the formula that we used in the experiment. We will calculate here the depression produced in the rectangular bar. So can anyone calculate and tell me what will be the depression produced in the bar when a load of 2 kg is suspended? So basically this is the situation. So this is the situation. So this is a rectangular bar. We are viewing from side. So this is a rectangular bar. This rectangular bar is placed in between two, supported at two ends. These are the supports, and then a load of 2 kg is suspended from it, from the middle. So this is a load. And this load is suspended. This is 2 kg. And we have size of the bar. The length of the bar is is 20 millimeter, 10 millimeter depth, and 1 millimeter is length. 1 meter is length. So the length of the bar is 1 meter. So this is 1 meter. And then the depth and height is 10 millimeter and width is 20 millimeter. And the weight of the load, which is suspended from its mid position, is 2 kg. Now the Young's modulus of the material is given here, 2 into 10 to the power 12 dynes per centimeter square, and we need to calculate the depressions. Now you can clearly see in the options the results are given in terms of millimeter. So here you need to convert all things into millimeter because here it is given in meter. So you can convert all into millimeter, or you can convert all into centimeter and then convert the answer into millimeter. It's up to you. So calculate and tell me what will be the correct answer among these four. Anyone calculated? So, if you see the formula, then the formula, to calculate the depression, it is, so it will be somewhat like this. So this is the depression and this is L. So this L is given by W capital LQ divided by 4y b dq. So here W is weight, L is length of the bar, breadth is B and depth is D. So weight is 2 kg. So 2 kg, when you convert it to, since all are in dyne and centimeter, so we will convert kg into gram, all into CGS unit. So 2 kg will be 2000 grams into, if you multiply 980, then it will convert into, so it is 2000 into 980. Then the length of the bar L is 1 meter, which is equals to 100 centimeter. Then Young's modulus Y is 2 into 10 to the power 12 times per centimeter square. Then breadth B is 20 millimeter. 20 millimeter means when you convert it into centimeter, it will be 2 centimeter. Then depth will be 10 millimeter or 1 centimeter. So when you put all these values in this equation, it will give us L equals to 2000 into 980 into 100 cube divided by 4 into y is 2 into 10 to the power 12 into 2 into 1 cube. So when you calculate it, it will be so when you calculate it will be 0. Since all are in centimeter, it will be 0.1225 centimeter. So when you convert it to millimeter, it will be 1.225 millimeter. So the correct answer is D. So now let's proceed to our next question. And the question says, if the temperature increases, the modulus of elasticity, whether it will decrease, increase, or remain constant. Can anyone tell me? If we increase the temperature of the substance, then its modulus of elasticity will increase or decrease? Yes, anyone? Can anyone tell me? If we increase the temperature of the substance, or if you heat a substance, then the modulus of elasticity will increase or decrease? Yes, anyone?
Decrease, sir.
Why? Can you tell me why it will decrease? Why it will decrease? It will decrease. Your answer is correct. But can you tell me why it will decrease? Why the modulus of elasticity decreases when the temperature is increased? So if you see, so in the formula for modulus of elasticity, what we have? Suppose this is modulus of elasticity y, suppose. Then this modulus of elasticity y is stress by strain. So the modulus of elasticity direct proportional to stress and it is inversely proportional to strain. So again, strain is what? Strain is nothing but delta L by L or delta V by V, whatever it may be. So this is the deformation and it is the ratio of deformation caused and the actual dimension of the object. So when you see here it gives when the temperature is increased. So when you increase the temperature, then what happens? If the temperature is increased, the force which was the force or the strength with which two molecules in a substance was being bonded or held together, then the force will obviously decrease because, for example, if you want to stretch a iron rod, then what you do? You need to heat it so that there will be easier. It will be easier for elongation or for deformation. So when you heat a substance or the temperature is increased, then corresponding to a particular stress, the strain is maximum or strain is increased. So when this is the iron rod, suppose when you heat the iron rod, then suppose initially when the iron rod was cold, then you are applying force F and the elongation was L only. And if you heat the rod, when you apply the same amount of force, then the elongation will be L prime and L prime will be quite high. So since L prime is quite high in comparison to L, then this delta L is high. So the strain will be quite high. So when the temperature increases, if the temperature increases, then the strain increases because the force of attraction between the two atoms or molecules due to which the body was bounded decreases. So when you increase the temperature, the strain will increase for a particular stress, the strain will increase. And then since the strain is inversely proportional to the modulus of elasticity, since strain is increasing, then modulus of elasticity will decrease. So when temperature increases, the modulus of elasticity will decrease. Is it clear to all of you? Okay, then towards next example. Now the next experiment was the measurement of spring constant of a given spring. Now you know whenever we suspend some object with the help of a spring, then it goes elongation or it goes deformation. But so due to this deformation, some potential energy is stored in the string because if you see, suppose if this is suppose you rotate it in vertical ways, so you rotate it 90 degree. So now see, suppose uh, this was the initial condition. This was the spring. Now, when you suspend some object, suppose this object has mass mg. It will suppose the object has mass m, so it will apply force of mg. So the potential energy is the mass of the body m. It was situated at a distance of x, but when it got elongated due to its force mg, then it moved a x and it is suppose this is touching to ground, then the potential energy here was something, suppose this potential energy was mgx, but here the potential energy is 0. Now this energy is stored here in this spring due to its stretching of the string. So this string or this spring will tend to come back to the original position. So it will exert a force in opposite direction. So now this force is directly proportional to displacement. The higher is the displacement, this force is called as restoring force. This force is called as restoring force because it will try to come back to its original position. So due to which it undergoes oscillation also, we will be discussing about it. So now when this restoring force will be directly proportional to this distance or the amount of elongation produced. Suppose here the elongation x is produced. So this restoring force F is directly proportional to x. As you can see, the elongation produced is in one direction, but the restoring force which is being acted is in another direction. So if you insert a proportionality constant, then there will negative sign will come into picture. So F is equals to minus kx. Since x and force, since the direction of elongation and direction of restoring force are different or they are opposite to each other, the negative sign is given here, and this constant is called as spring constant K. So basically, this constant gives an idea about the rigidity or strength of the spring. And if the strength is more, then it will exert more force and it will try to come back to its original position. So here, as you can see, the negative sign indicates that the reaction force is pointing in the opposite direction. So the force is in one direction and the elongation in another direction. So this is the restoring force of the spring, which is directed towards equilibrium. And this is the unit of spring constant. As you can see, spring constant is F Newton, and this is meter. So Newton per meter is spring constant unit, and this is the, as you can see, the potential energy stored in the spring is kx. So now this is the mgx and it is 0. So this potential energy mgx is stored in the spring, and the energy stored in the spring is called as half kx square. So if kx is the force, then if you calculate the energy is f dx minus f dx, the energy. So you calculate kx dx minus here. So when you calculate, it will be half kx square. So the potential energy stored in a spring is half kx square. So now let's solve a few problems. Now the question says the frequency of a oscillation of a particle of mass m suspended at the end of a vertical spring having a spring constant k is directly proportional to. So suppose this is a rigid support and the spring is elongated with a mass. This is the mass. The mass is m. So it will exert a force mg, and this is the spring constant k. Now, since due to the property of the spring, the energy due to the energy stored, it will try to come back to its initial position. So it will, the force will act upon this, and then this load m will undergo oscillation because the till the reaction force is balanced by this force mg or weight mg, then till then it will be oscillating. So we need to find out what is the frequency of oscillation, because it will oscillate and then it will, due to its weight, it will try to come back to its original position. So in this way, the spring will the energy will be stored, it will contract, then it will expand, contract, expand like this. Then due to which this load, it will undergo oscillation like this. It will undergo oscillation. So now this it has a frequency of oscillation. Now this frequency of oscillation will be proportional to what k. It will be mk or m by k, m square by k or k by m root over. So if anyone have any idea, try to solve it and tell me what will be the dependency of the frequency upon this ratio, or what will be the type of dependency. It will, whether it will depend upon the ratio or whether it will be depend upon the product or what.
Sir, under root k by m.
Okay, so how you can say it will be under root k by m?
Sir, omega square equal to k by m.
Okay. So let others try and then we'll discuss. Please everyone mute themselves. Let others try and then we'll discuss. So now this will undergo oscillation. So this is equivalent to simple harmonic motion, and we know the equation of motion of simple harmonic oscillation is given by d square x by dt square plus omega square x equals to 0. Now here, if you calculate, the equation will come d square x by dt square plus k by m x equals to 0. So if you compare, then this omega square will be k by m, or omega will be k by m root over, or frequency. Frequency we know omega is 2 pi f. So f will be 1 by 2 pi into k by m root over, or to the power half. Similarly, if you compare it to a problem of simple pendulum, in simple pendulum, you know this omega square was what? L by g root over equals to omega. In case of simple pendulum, so similarly here, this length is replaced by the spring constant k, and this total length is replaced by the spring constant k, and the weight here, the mass is replaced by this g is replaced by the mass of the body. So if you see, the frequency will be directly proportional to k by m root over. So basically here, now I'd like to say a few things about equilibrium. Now if you see, suppose there are two situations. This is one situation, this is another situation. Suppose one ball is placed here, another ball is placed here. So if you apply some force here, what will happen? The ball will go downwards, but here if you apply some force, then the ball will go up and then it will come back. So it will oscillate. So for this ball, this position is unstable equilibrium. Unstable equilibrium. But for this ball, the position here is stable equilibrium. So when we apply or when we disturb the body in its unstable equilibrium, then it does not undergo any type of oscillation. But when you apply some force or disturb the body at the position of stable equilibrium, but since here the stable position is, it will tend to come towards ground. So since we are applying some force and this is being stored, the energy is being stored in this spring, it is undergoing oscillation. So when we apply some force on a body at stable equilibrium, then it undergo oscillation. And also there is a concept of small oscillation. You will be studying about it. But also if you this k, in case of this small oscillation, it's now this is so when the body changing its position, then there is change in potential energies. Potential energy here, the potential energy decreased. Here the potential energy will increase, decrease like that. So it will undergo a change in this potential energy. So now if potential energy is V, then this K is also this K is also represented as del square V by del x square at x0. This x0 is the stable equilibrium point. So suppose there is a potential given, so you can easily calculate what will be the frequency of oscillation if some force is applied. So this is the other type of question. So now this is the correct answer. Also, if you compare it with the dimension, then directly without any calculation, you can say that the dimension of k by m to the power half matches the dimension of frequency, because here 2 pi has no dimension, so it will be a k by m square root. So now next question is, a 10 kg metal block is attached to a spring of spring constant 10 to the power 3 Newton per meter. The block is displaced from equilibrium position by 10 centimeter and released. The magnitude value of maximum acceleration of the block is. So here the 10 kg metal block is attached to a spring and the spring constant is 10 to the power 3 Newton per meter. Then the block is displaced from equilibrium position by 10 centimeter. Suppose So as you can see, it was in equilibrium, but we displaced it or we disturbed it, then it will undergo oscillation. So when you undergo oscillation, there will be some acceleration because since the body is oscillating along the direction or opposite direction of gravitational field, then it will be having some acceleration. So we will calculate the acceleration here. So it is pretty much similar to the previous types of. It is very easy. So if you calculate and tell me what will be the maximum acceleration of the bird.
Sir, option A, 10 meter per second square.
So how you calculated? How it will be 10 meter per
Sir,
second?
we, we know that x equal to a sine omega t. Then if we
Okay.
differentiate this, then we get the velocity, and if we further differentiate this, then we get the acceleration, which is a omega square sine omega t, and a sine omega t is equal to x. So a equal to omega square x.
Yes. Okay.
And
So
omega square equal to 100.
okay, I got it. Any other student who have calculated? So, um, so one of your friend uh, told how to calculate in terms of oscillation, but simply without considering any oscillation, because here if you see the question, there is no oscillation here mentioned. So simply we can calculate. So from Hooke's law, we know the force is direct proportional to x, or for a spring, the force is known as F is equals to minus kx. So if you take the modulus of the force, because here the acceleration are given, the only the dimension of the acceleration is on the values of the accelerations are given, but there are no sign involved. So simply we can take the magnitude of the force is kx. Now from in previous question you had to calculated omega square equals to k by m. We have calculated in previous question. So k is m omega square. So when you put this value of k here, then it will give us f is equals to m omega square into x. Now we know force is equals to mass into acceleration is equals to m omega square x. Then if you m on both sides, it will be a simply omega square x. So here when you calculate. How do you calculate omega? Omega is k by m. So k is given. This is k. K is 10 to the power 3 Newton per meter, and the x is given 10 centimeter, and the mass of the metal block is given 10 kg. So when you calculate, then omega will be k by m root over, or omega square will be simply k by m. So omega square will be 10 to the power 3 by 10. It will be 10 to the power 2. So putting the values, a will be 10 to the power 2 into 10 centimeter will be 0.1 meter. It will give us 10 meter per second square. So this will be the value of maximum acceleration of the block. Is it clear to all of you? Yes? Anyone? Is there anyone who has any doubt? Okay, so let's proceed towards next question. Now, the question says when a mass m is attached to a spring, it normally extends by 0.2 meter. The mass m is given a slight additional extension and released. Then its time period will be. Now it is pretty much similar to the previous questions we have solved. Here, the normal extension or x is 0.2 meter. But when you give it some other additional extension or you disturb it, then it will undergo oscillation. As I said you, it undergoes oscillation. So what will be the time period of this oscillation? So here the value of g is given. And tell me calculating what will be the time period of oscillation. But here you can see the mass m is not given. So you need to derive the equilibrium condition or derive the equilibrium condition. Like here, like in previous case, in case of simple pendulum, this k by m was equal to L by g. So here you can similar way, by considering the equilibrium, we can calculate that will be the extension. Since the extension is given, we can calculate the time period of oscillation. Anyone calculated? So now you see, now there is a string and there is a load here. This load, it is exerting force mg, and the force acting upon the spring due to the spring constant k and the elongation x. Because when it is in equilibrium position, the spring is stressed with or through by a distance x. So we know the force is kx for the spring, and here this weight mg is equivalent to the force. So under equilibrium condition, when there is some distance, sorry. So suppose the mass is suspended from the spring. So when the mass gets suspended, then it will undergo oscillation. Then eventually, after a few oscillations, it will come to its rest position or equilibrium position. So in that equilibrium position, this weight mg will be balanced by the force. This force in the spring is kx. So under equilibrium condition, we can say this kx is equals to mg. So we know this k by m will equal to g by x. Now we know time period. Time period is equals to uh, so omega is equals to 2 pi by t. So time period is equal to 2 pi by omega. It will be 2 pi by omega means k by m root over. It will be 2 pi into m by k. But here m by k is equal to x by g. So it will be 2 pi into x by g root over. So when you put the values x here, x is 0.2 meter and g is 9.8 meter per second square. Here it is given 980 centimeter per second square. But since the you can easily convert it to meter to centimeter, or you can convert g from centimeter per second square to meter per second square. So in any way, it will come 2 pi into x is 0.2 divided by 9.8. So it is 2 pi into 1 by 49 square root. It is 2 pi by 7 second. So the correct answer is 2 pi by 7 second. This is the time period. Now another question. A spring balance scale reading from 0 to 15 kg is 10 centimeter long. A body is suspended from the spring is found to be oscillating with a frequency of 2 oscillations per second. How much does the body weigh? So it is similar to the kinds of question we have discussed. Here it says the spring balance, the reading from 0 to 10, which gives the reading from 0 to 15 kg, 10 centimeter long. So this is the spring, and there will be some weight here. So when the weight is 0, the stretching of the spring x is 0, but when the weight is 15 kg, the stretching is 10 centimeter, because here it is given the spring balance scale, the reading from 0 to 15 kg is 10 centimeter long. It gives reading from 0 to 15 kg and it is 10 centimeter long. So when it is 0, there is no extension in the spring, but when there is 15 kg load, then the extension of the spring is 10 centimeter. So this body, suppose any body, this is suspended and it is oscillating with a frequency of 2 oscillations per second. So the frequency of oscillation is 2. Then what will be the weight of the body here? So anyone calculated what will be the weight of the body? So basically in the previous question, as you can see here, we calculated the time period is 2 pi m by k root over. So the time period of oscillation T is 2 pi m by k root over. So the frequency of oscillation will be how much? The frequency will be 1 by 2 pi k by m root over. Here the frequency is given. We need to calculate m. So this m is unknown for us. So if you see, so we need to find out k, because when we find out k, then putting the values of k and f, we can calculate the value of n. So how we will find out k? So in previous case, this was the equilibrium condition. So similarly here it will be. So since the spring balance reads from 0 to 15 kg when it 10 centimeter long, so this 15 kg equal to 10 centimeter length. So 15 kg produces an stretching or elongation of 10 centimeter. So when it converted into force, then it will be 15 into 9.8, and this is equals to spring constant k into elongation 0.1 meter. So when we calculate from this k will be how much? 15 into 9.8 into 1 by 0.1. So when we put this value of k here, what we will get? F will be 2 is equal to 1 by 2 pi. Value of k here we will put, then root over. So when you put all the values, m will be how much? So m will be 2 square 1 by 2 square into 1 by 2 pi into value of k, 15 into 9.8 into 10 or 1 by 0.1. So it will, when you calculate it, it will come 9.31 kg. So when we suspend a weight of 9.31 kg, then it will undergo oscillation with a frequency of 2 oscillations per second. Is there any doubt in this question? Okay, so let's move towards next question. So now this question says find out the equivalent spring constant of two springs when they are connected in series and when they are connected in parallel. So suppose there are two springs. This spring has spring constant K1 and this spring has spring constant K2. Suppose these spring are connected in series. Series means this is a rigid support, then this is a spring, and then another spring is connected with it in series, and there is a load mg. So this is K1, this is K2. So this is the case for series. And when you consider parallel combination, then from parallel combination means both the springs are suspended from similar rigid support and they are connected each other, and there is a load here mg. So this is parallel combination. So what will be the equivalent spring constant of these two springs connected in series here, and what will be the equivalent condition of the equivalent spring constant of the two springs? This is K1, this is K2 connected here. So what will be K equivalent here, and what will be K equivalent here? It is a very good question. Also, there is some physical similarities between the spring and some other device which we have discussed. So if you can answer it, then I will tell you what is the similarity between the spring and the device I am saying. Yes, can anyone tell me? So if they are connected in series, what will be the equivalent spring constant? And if they are connected in parallel, what will be the equivalent spring constant? Now let's calculate. So since there are two springs and they have different spring constants, so for a particular weight, there will be two different types of displacements here. Due to this spring, the displacement, suppose it is x1, and due to this spring, the displacement is x2. So since both the springs are connected to a load and they are in series, so you can say the force which is equal to kx. So this force will be equal to minus k1 x1, and it will be also equal to minus k2 x2. So when there are combinations, then suppose we multiply k1 on both sides, then k1f will be minus k1 k2 x2 and k k2f will be minus k1 k2 x1. Now since as you can see here there are two springs, so and there since they are connected in series, so this x1 will be x2. So this x1 is equals to x2 here. So since this x1 is equals to x2, so when you add these two force, it will be f k1 plus k2, which will be equal to k1 k2 x plus k1 k2 x. So since this x1 and x2 are equal, so the total elongation will be x1 plus x2 here. It will be 2x since x1 is equal to x2. So if you compare, f will be 2 k1 k2 divided by k1 plus k2 into x. So this is the expression for this spring. So if you compare, the elongation is 2x here. So if you replace this combination with a single spring k, then what will be the spring constant? Then the spring constant will be k1 k2 divided by k1 plus k2. So this is the equivalent spring constant of two springs k1 k2 connected in series. Similarly, if they are connected in parallel, then what happens? If they are connected in parallel, then the elongation will be, suppose elongation is x in both the cases. So the weight will be, suppose this is force F1 for the spring will be minus K1x, and the force F2 for the spring will be minus K2x. Then these two forces are being balanced by this load mg. So when you here, this mg will be F1 plus F2. So mg will be K1x plus K2x, because this under balance condition mg plus f1 plus f2 equal to 0. So when you bring f1 and f2 to right hand side, then the negative sign will disappear. It will be mg is equals to k1 plus k2 into x. So since here there is x and here there is x and both are connected in parallel, so the total elongation here will be x. So if you compare f direct proportional, f is equal to minus kx here. This f is here mg. So total f is that equal to k1 plus k2 x. So when you compare these two, you will find this k equivalent will be k1 plus k2. If you see here, when two springs are connected in parallel, and their spring constants are simply added to with each other, that is k1 plus k2. But here, if the spring are connected in series, the spring constant is k1 k2 divided by k1 plus k2. So if you see here, this combination of spring is exactly equal to the it is the combination of the spring is behaving exactly equal to as if they are capacitors, because for capacitors, when two capacitors of capacitance C1 and C2 are connected in series, we get the equivalent capacitance is K1 K2 C1 C2 divided by C1 plus C2, and for parallel combination they are added. So we can say the function of capacitor and the function of spring is pretty much there are similarities between a capacitor and a spring. If you compare, the capacitor stores electrical energy, but the spring here stores mechanical energy. So the potential energy is stored in form of stretching of the string. So since when the spring is stretched and we disturb the equilibrium position, it undergoes oscillation. Similarly, if we connect a capacitor in a circuit, then it will also result in oscillation of the charge, because the current will capacitor will charge for one time period, then it will discharge. So the current will oscillate in the circuit. So you must have heard about LC oscillations, RC oscillations. So basically, when there is capacitor in a circuit, it drives oscillation. So when is spring in a device, so it also drives oscillation. So capacitors and springs behave more or less in same way. One stores mechanical energy and another stores electrical energy. So now let's move towards the third question, third experiment of today's session. This experiment was about measurement of moment of inertia affect highway. Now we know the moment of inertia, the role moment of inertia plays is similar to the role played by moment of inertia in rotational motion is pretty much similar to the role played by mass. So since mass is equal since in motion mass is related to inertia, so here in rotational motion moment of inertia related to inertia, or the resistance of a body to change its rotational motion. Since in linear motion it was the mass of the body which was providing resistance to its linear motion, so in moment of inertia it gives the resistance of motion to change of its rotational motion. Resistance of a body to a change in its rotational motion. And this is the formula for moment of inertia. I is summation over mi ri square. Now here, if the weights are distributed in distinct manner, so we can take summation. But if the weights are in continuous distribution, then this integration sign, this summation sign is replaced by this integration sign, and we can say that this I is integration di, which is equals to integration m or the dm r square. It has something value total mass to the. So and there is another quantity which is important in case of moment of inertia. This is radius of gyration. So radius of gyration, like in, so you must have known about center of mass. So radius of gyration is somewhat like that. So radius of gyration is the radial distance from the given axis of rotation where the entire mass of the body can be assumed to be concentrated so that its rotational inertia remains unchanged. So suppose this is a body and we suppose this is the axis passing through the body, and we calculate the moment of inertia of the body, and the moment of inertia is m r square. So suppose when this moment of inertia will be equal to the particular consideration case of moment of inertia. So suppose if we consider this whole mass m is concentrated here, and the distance from this mass to the axis is k, then if the moment of inertia I is equals to m r square, then this will be k square mk square, and this k is radius of gyration. So the total mass of the body is concentrated at a particular point, and this point is situated at distance k from its axis of rotation around which the moment of inertia is calculated. So also there are two theorems which are used in calculating moment of inertia. One is parallel axis theorem, another is perpendicular axis theorem. This is parallel axis theorem. So parallel axis theorem says, what parallel axis theorem says, the moment of inertia I will be ICM plus m d square. So the moment of inertia, suppose the moment of inertia through this axis is ICM, and the moment of inertia of an axis which is parallel to that axis and is at a distance d from the initial axis, then the moment of inertia will be equals to mass into the distance between the two axes. So the I equal to ICM plus md square, and here it is perpendicular axis theorem. It says the moment of inertia IA, which will be equal to the sum of moment of inertia of any axis which are perpendicular to it. So now these two axes are parallel. These two axes are perpendicular to this IA. So the moment of inertia of the body with respect to this axis A is equal to the sum of the moment of inertia of the body about this axis B and about this axis C. So this is perpendicular axis theorem when these axes B and C are perpendicular to A. Now there are few quantities and we want to calculate the moment of inertia. So for a solid cylindrical disc, the moment of inertia is half mr square. Now you can see here the axis is different and here the axis is another axis. So here we have applied so this half mr square. So this there will be 1 by 4 plus because this axis is perpendicular to it. So it will be 1 by 4 plus 1 by 4, 1 by 4, and the relation here it is 1 by 12 ml square. So this the central moment of inertia is 1 by 12 ml square. So here the central moment of inertia is 1 by 12 ml square, and the and corresponding to this parallel axis theorem, this 1 by 2 ml square divided by 2, because here it was sum, so it will be I will be what? I will be IA by 2. So this 1 by 2 by 2 is 1 by 4, and this corresponds to this 1 by 12 ml square. Now for a particular ring, moment of inertia is mr square for this axis, and for this from parallel axis theorem, the perpendicular axis theorem, it is by 2, it is half. So there are for solid sphere it is 2 by 5 mr square, and for thin spherical cell it is 2 by 3 mr square. And for a rod, the moment of inertia passing through this axis, which is passing through its center, is 1 by 12 ml square. But here it is 1 by 3 ml square when the rod is placed here. So there are a few objects whose moment of inertia is calculated. There are some ways to calculate the moment of inertia. You can also refer to any book how they are calculated. So now we will solve a few problems related to the calculation of moment of inertia of a system. Now this question says there are three rods, each of mass m and length L, are joined together to form an equilateral triangle as shown in figure. Find the moment of inertia of the system about an axis passing through its center of mass and perpendicular to the plane of the triangle. So this is a triangle ABC. This length is L. This is also L. So both all the sides of this triangle are of equal length, and here it is said to find the moment of inertia of the system about an axis passing through the center of mass and perpendicular to the plane of triangle. So the center of mass, since all are equal, the center of mass will lie exactly at the middle of the triangle. So suppose this is the triangle, and we need to find we need to find the moment of inertia around this axis, because it is perpendicular to the plane of the triangle and is passing through its center. So can anyone tell me what will be the moment of inertia for this case? For this triangle, what will be the moment of inertia which is passing through the center of mass? Yes, anyone calculated? So now we know this is a rod, and for a rod, the moment of inertia of the rod passing through its this position is 1 by 12 ml square. So for a single rod, this is the rod, and the moment of inertia of the rod passing through this axis, the moment of inertia of the rod with respect to this axis is passing through center is I is equals to 1 by 12 ml square. Now, if you compare this axis and this axis, so that this axis was passing to this point, and but here the axis is passing to this point, and they are parallel. So we can apply here parallel axis theorem. So according to the parallel axis theorem, if there are two axes and there is some distance d between the axis, and there is I c here, this is I1, then I will be I1 plus md square, is not it? So since I is 1 by 12 ml square, so then for this particular side or a single rod, suppose this is AB, for this AB it will be 1 by 12 ml square plus mass into the distance between these two axes. So IAB will be 1 by 12 ml square plus m into d square. Now, if you calculate for a equilateral triangle, the distance between this point to this point, it will come out to be 1 by 2 root 3. So, so it will be coming out to be L 1 by 2 root 3 into L. So it will be 1 by 12 ml square plus m into L by 2 root 3 square. So it will be ml square by 6. So this is ml square by 6 for AB, ml square by 6 for AC, and ml square by 6 for BC also. So if you calculate, I total will be how much? IAB plus IAC plus IBC. It will be both will be equal, and all will be equal, and they will be equal to ml square by 6. It will be ml square by 2. So the moment of inertia of this particular triangle, which is passing through its center and is perpendicular to its plane, is half ml square. Yes, is there any doubt in this question? Anyone? So today we'll stop here. Then in next session we'll discuss a few more problems related to this moment of inertia, and we'll calculate moment of inertia under different conditions, and then we will carry on our discussion related to other experiments. So yes, is there anyone who have any doubt? Yes. So I think we should stop here, and we will meet on next Saturday. Thank you all.